Hi, I'm Erica Bertolini from the University of Genova, and I'm working in collaboration with Nicola Maggiore. Today I'm going to present the holographic projection of electromagnetic Maxwell theory. So, the first appearance of a boundary in field theories is for the Casimir effect, but only many years later, semantic formalized the concept of boundaries in quantum field theories, as the surface separating the space in half, so requiring the separability of the propagators. But the most relevant examples showing the great importance of boundaries should be searched in the context of topological field theories, which are really interesting theory in mathematical sense, but have no physical content of their own, being defined by null Hamiltonian and energy momentum tensors. But when we introduce a boundary on these theories, we find local observables, so we can extract an interesting physical content. And for this, various examples can be made. First of all, the Chen-Simons theory, which is a three-dimensional theory, is really interesting because due to the presence of the boundary, we can extract the degrees of freedom of the fractional quantum Hall effect. A similar case is for the BF theories in 3 and 4 dimensions, for which the physical content regards topological initiators. In a completely different context, the ADS-CFT correspondence is now giving interesting results in the field of condensed matter theory, specifically for superconductivity and strange metals. But what is still lacking is the study of a boundary in a theory for which the bulk already has a physical content, and which is the theory for which the bulk has probably the most known physics, if not the Maxwell theory. And what happens if we add a boundary on the 4-dimensional Maxwell theory? Do we have any degrees of freedom? Are there conserved currents? Do they form an algebra? Is there a 3-dimensional holographic counterpart of a Maxwell theory? So, from all these questions arises this work, and so we decided to study the 4-dimensional Maxwell theory with boundary. And now let's start. So the introduction of the boundary is done by including a theta term, a Heaviside step function, inside the action. Thus, in this case, the role of the boundary is played by x3 equals to 0, so we have a planar boundary, and the theory is confined in half space. A first remark must be made in this case, because due to the presence of the boundary, on this boundary we have two independent fields, which are not only the gauge field A, but also its normal derivative with respect to the boundary, which we called A tilde. For this fact, we must add a second external source term in the action, which is this one, and which must be only on the boundary. For the presence of the boundary, we must include another term in the action, which must be compatible with power counting and Lorentz invariance, and which must exist only on the boundary. So this is done by the introduction of this delta term. Now we have all the pieces to compute the equation of motion of the theory, and from this we can extract, by using a variational principle, the boundary condition of the theory. First observation is that, in this case, the boundary conditions are not put by hands, but is the theory itself giving us these boundary conditions. So, from the equation of motion, we can also compute the word identities, which, due to the presence of the boundary, are broken by these right-hand side terms. And the first interesting result is given by going on shells, so at vanishing external sources, for which we find two conserved currents. And thanks to these two equations, we can define two vector fields living only on the boundary, which are given by the most general solution to these two equations. Now, the correct degrees of freedom of our theory can be found only by defining new bulk fields in this way, by a linear transformation, and so we also have new boundary fields in this way. This relation is interesting because it's invariant under gauge transformation on the boundary fields. This is telling us that also our three-dimensional theory should be gauge invariant theory. So from this new definition, and by a functional derivative of the word identities with respect to the external sources, we can find a commutation relation of this form, which is an abelian Kac-Moody algebra, for which the central charge is this. And so, due to the unitarity of the conformal field theories, we have this constraint on the parameter of the transformations. And a first interesting thing is the fact that, depending on the values of these parameters, we have different conformal field theories. So now, what do we want to do with this Kac-Moody algebra? Well, we want to rewrite it in terms of canonical commutation relations. So we can extract the canonical variables of the theory and find the dynamics of our three-dimensional theory. So the three-dimensional theory can be written by following three important steps. First of all, we must ask the 3D action to be gauge invariant action under these transformations. Second, its Lagrangian must respect this relation, which is given by the identification of the canonical variable we found from the Kac-Moody algebra. Last but not least, the equation of motion of the three-dimensional action must be compatible with the boundary conditions we found from the bulk theory, so we can realize the so-called holographic contact. So, from the first 2 points, we find this three-dimensional action and also a constraint on the dimension of the bulk boundary fields, which should be of massive dimension 1/2. So now we found these 2 equations of motion, and we must do this holographic contact. Can it be done? Yes, it can be done in 2 inequivalent ways, which involves the curl of the boundary conditions. And surprisingly, these 2 inequivalent holographic contacts gives us 2 equivalent actions. And by requiring the positivity of the energy density of this action, we also find a constraint on the parameters of the transformation, which is the same we found by requiring unitarity of the conformal field theories, so a positive central charge. Finally, the three-dimensional action from both holographic contacts is this, which have a topological term with massive coefficient, and for which the equations of motion are these. An interesting thing is that, despite the similarity with the Maxwell-Chern-Simons action, we computed the propagators of this theory, and it appears that this is a massless theory. So, differently from the massive Maxwell-Chern-Simons action. So, in conclusion, we do found physics on the boundary of the Maxwell theory, and this has some analogies with the topological field theories with boundary. First, we found 2 concept currents, and these define the Kac-Moody algebra. More than this, we also found a new three-dimensional massless gauge theory with a topological term, and finally, we also found a link between the positivity of the energy density of this three-dimensional theory and the unitarity of the conformal field theories. So, what can we do now? Well, first of all, we must understand what is the physics of this three-dimensional action. A hint could come from the topological insulators, which are defined by two conserved currents, as we found in this case. So we could think that four-dimensional Maxwell theory could be a possible bulk effective theory for these materials. But we could even extend this study in a more general sense, for example by studying a four-dimensional Maxwell theory in cubed space with a cubed boundary, or even a non-abelian case, so a four-dimensional Maxwell Young-Mills theory with boundary. Even more, we could study a five-dimensional Maxwell theory, or maybe a Young-Mills theory with boundary. So, which could have interesting results. And this is all. Thanks.